Section 1 Introduction. We're here to introduce a new development in the field of natural language processing, NLP. The landscape of NLP has been significantly transformed by the introduction of large-scale language models, LLMs. These models have shown remarkable performance in a variety of tasks, enhancing our ability to understand, generate, and interact with human languages using computational methods. Historically, the development of language models has primarily focused on transformer architectures. Well-known models like the vanilla transformer, GPT series, BERT, and BART have become standard frameworks in related fields. The success of these transformer architectures is largely due to the softmax attention mechanism. This mechanism identifies relationships between input tokens in a data-driven way and is aware of their global position. This allows the model to effectively handle the complex dynamics of natural language. However, traditional transformers have their limitations. The main issue is their quadratic time complexity in relation to the sequence length, which restricts their scalability and efficiency. This can lead to increased computational resources and time during training and inference stages. Many efficient sequence modeling methods have been proposed to reduce this quadratic time complexity to linear. But these methods often fall short in two areas. They don't perform well in language modeling and they don't show speed advantages in real-world situations. In this paper, we present TransNormerLLM, the first linear attention-based LLM that outperforms conventional softmax attention in both accuracy and efficiency. We've built upon the foundations of the previous linear attention architecture, TransNormer, and made a series of advanced modifications to achieve superior performance. These enhancements include positional embedding, linear attention acceleration, gating mechanism, tensor normalization, and inference acceleration. One significant improvement is the substitution of the TransNormer's diag attention with linear attention to boost global interactions. To tackle the problem of dilution, we introduced LRPE with exponential decay. We also introduced lightning attention, a new technique that greatly speeds up linear attention during training, resulting in more than double the improvement and reducing memory usage by 4 times with I/O awareness. We simplified GLU and normalization, with the latter leading to a 20% overall speedup. A robust inference algorithm ensures the stability of numerical values and constant inference speed, regardless of the sequence length, thereby enhancing the efficiency of our model during both training and inference stages. To demonstrate the effectiveness of TransNormerLLM, we've collected a large corpus that is over 6 terabytes in size and contains more than 2 trillion tokens. We've developed a new self-cleaning strategy to filter the collected corpus to ensure data quality. We've expanded the original TransNormer model ranging from 385M to 175B parameters as shown in the table and conducted a series of comprehensive experiments and ablations on our corpus. The results show superior performance to softmax attention-based methods as well as faster training and inference speed. We're dedicated to promoting community-driven advancements in the field of LLMs. As part of this commitment, we plan to make our pre-trained models available to the public. This will allow researchers and practitioners to build upon our work and explore efficient transformer structures in LLMs. Section Summary. The introduction highlights the significance of large-scale language models, LLMs, in natural language processing, NLP, and the limitations of conventional transformer architectures due to their quadratic time complexity. The paper introduces TransNormerLLM, a linear attention-based LLM that surpasses softmax attention in both accuracy and efficiency. It incorporates advanced modifications such as linear attention acceleration, gating mechanism, tensor normalization, and inference acceleration. The model is validated through comprehensive experiments on a large corpus, and the authors plan to open source their pre-trained models to foster community-driven advancements in LLMs. Section 2 Related work. We've been closely following the advancements in the field of large language models, LLMs, in recent years. The trend has been towards creating bigger and more complex models, with some boasting over 100 billion parameters. Examples of these include GPT-3, Gopher, PaLM, and GLM. There are also specialized models like Galactica, designed for specific areas such as science. One model that stands out is Chinchilla, which has 70 billion parameters. What makes it unique is that it focuses on the number of tokens rather than the weight of the model, challenging the traditional scaling laws. Another model that has caught our attention is Llama, which has shown promising results and is available as an open-source project. The conversation around LLMs also includes the dynamics between open-source and closed-source models. Open-source models like Bloom, Opt, Llama, Pythia, and Falcon are emerging as strong competitors against closed-source models like GPT-3 and Chinchilla. To speed up the training process, sparse attention was introduced, but so far, only GPT-3 has adopted it. Despite the popularity of transformer-based large models, there's a growing interest in addressing their square spacetime complexity. This has led to the exploration of different model architectures that move away from the traditional transformer structure. 4 models that have shown promise are linear transformers, state space models, long convolution, and linear recurrence. These models are favored because they offer better time complexity and competitive performance. The linear transformer is one such model. It breaks down softmax attention into the form of the inner product of hidden representations. This allows it to use the right product trick, where the product of keys and values is calculated to avoid creating a quadratic n by n matrix. Different methods use different hidden representations. For instance, some use 1 plus ELU as an activation function, others use the cos function to approximate the properties of softmax, and some approximate softmax through theoretical approaches. Although the theoretical complexity of linear attention is O(n times d squared), its actual computational efficiency can be quite low when used in causal attention due to the need for cumsum operations. Moreover, most linear transformers still have a performance gap compared to traditional transformers. Section summary. In recent years, there have been significant advancements in large language models, LLMs, with models like GPT-3, Gopher, PaLM, and GLM having over 100 billion parameters. Specialized models like Galactica and Chinchilla have also emerged for specific domains. Open-source models like Bloom, Opt, Llama, Pythia, and Falcon are competing against closed-source models like GPT-3 and Chinchilla. Sparse attention was introduced to speed up training, but only GPT-3 adopted it. Additionally, there are alternative non-transformer-based LLMs like linear transformers, state space models, long convolutions, and linear recurrence, which offer superior time complexity and competitive performance compared to traditional transformers. However, these alternatives still have a performance gap compared to traditional transformers. Section: State Space Model. We're going to discuss 3 different models: the state space model, long convolution, and linear RNN. The state space model is a sequence modeling method that uses a specific equation known as the state space equation. This model is designed with unique initialization, diagonalization assumptions, and techniques that allow it to perform on par with transformers. One of its key features is that it allows for inference to be conducted with a constant level of complexity. Next, we have the long convolution model. This model uses a kernel size that's equal to the length of the input sequence, which allows it to consider a broader context than traditional convolutions. Training these models involves the efficient fast Fourier transforms (FFT) algorithm, which has a complexity of O(n)log(n). However, there are some challenges with long convolutions, such as the need for causal convolution inference, which requires storing all past computations in a manner similar to the key value (kv) cache used in self-attention (SAW). The memory requirements for handling long sequences, along with the higher inference complexity compared to recurrent neural networks (RNNs), make them less ideal for processing long sequences. On the other hand, linear RNNs are more suitable for long sequence modeling as replacements for self-attention (SAW). A good example of this is the RWKV model, a linear RNN-based language model (LLM) that has shown competitive performance against similarly scaled GPT models. Now, let's talk about some improvements we've made to the architecture. We've carefully examined each module of the network and proposed several enhancements to strike an optimal balance between efficiency and performance. We'll discuss the key designs of each block and the reasoning behind each modification. We've also conducted an ablation study on each of these modifications. One of the improvements we've made is to the position encoding in the TransNormer model. In the original model, diag attention is used at the lower layers to avoid dilution issues. However, this leads to a lack of global interaction between tokens. In our improved model, which we call TransNormerLLM, we use linearized relative positional encoding with exponential decay, LRPED, to address this issue, retaining full attention at the lower layers. The overall expression of our position encoding is a multiplication of the top query and key, multiplied by lambda raised to the power of the difference between the positions, and multiplied by the exponential of I times theta times the difference between the positions. We set theta to be learnable. This position encoding is fully compatible with linear attention, as it can be decomposed with respect to the positions separately. The value of lambda for the HTH head in the LTH layer, assuming there are a total of H heads in L layers, is given by the exponential of -8 times the head number divided by the total number of heads, multiplied by 1 minus the layer number divided by the total number of layers. This ensures that the theoretical receptive fields, TRF, at the lower layers is smaller compared to the higher layers, which aligns with TransNormer's motivation. It's important to note that the decay rate in the last layer is set to 1, allowing each token to attend to global information. We choose lambda to be non-learnable since we empirically found that gradients become unstable when lambda is learnable, leading to NaN values. Section summary. The state space model is a sequence modeling approach that achieves performance similar to transformers while enabling inference with constant complexity. Long convolution models provide a wider context but have challenges in terms of memory requirements and higher inference complexity. Linear RNNs, like the RWKV model, are more suitable for long sequence modeling and have shown competitive performance against GPT models. In the proposed TransNormerLLM architecture, improvements are made to the position encoding module using linearized relative positional encoding with exponential decay, which allows for global interaction between tokens while retaining full attention at lower layers. Section 3.1.2 Improvement 2, Gating Mechanism. In the second improvement of our model, TransNormerLLM, we've incorporated a gating mechanism to enhance its performance and streamline the training process. We've borrowed this approach from Flash and used the gated linear attention (GLA) structure in token mixing. In simpler terms, we've mixed tokens in a way that involves a gating mechanism, which is a method of controlling the flow of information. The mathematical expression for this process involves a few variables. We have Q, K, V, and U, which are all derived from the input X and different weight matrices. We've chosen a specific function, called phi, to be 1 plus ELU, which is a type of activation function. However, we found that the choice of phi doesn't significantly affect the results. To speed up the model, we've proposed a simplified version of GLU, gated linear unit, which we call simple GLU, SGLU. This version removes the activation function from the original GLU structure, as the gate itself can introduce non-linearity. This simplification leads to a new way of mixing channels, which involves V, U, and a weight matrix, W. We've found that not using an activation function doesn't result in any loss of performance. In the third improvement, we've used a technique called tensor normalization. We've used norm attention, which is a type of attention mechanism that eliminates the need for softmax and scaling operations. This mechanism can be transformed into a linear form, which allows for efficient recurrent prediction. In this process, we only update a specific part of the attention matrix, which makes it more efficient. In TransNormerLLM, we've replaced the RMS norm with a new simple normalization function called simple RMS norm, or SRMS norm for short. This function normalizes the input by dividing it by its 2 norm divided by the square root of the dimension, d. We've found that using SRMS norm doesn't lead to any loss of performance. The overall structure of our model involves 2 main steps. First, the input X is updated using gated linear attention, GLA, with SRMS norm normalization. Then, it goes through the simple gated linear unit, SGLU, with SRMS norm normalization again. This structure improves the model's performance based on the pre-norm approach. The pseudocode for this process involves updating X with GLA and SGLU, both of which involve SRMS norm normalization. Section summary. In this section, we introduce 2 improvements to the TransNormerLLM model. The first improvement is the use of a gating mechanism called gated linear attention, GLA, and simple GLU, SGLU, to enhance model performance and accelerate training. The second improvement is the adoption of norm attention and simple RMS norm normalization functions to eliminate the softmax and scaling operation, resulting in a more efficient linear attention mechanism. The overall structure of the model involves applying GLA and SGLU with simple RMS norm normalization in consecutive steps, leading to improved performance based on the pre-norm approach. Section 3.2.1 Lightning Attention. We're going to discuss 2 key aspects of our research: lightning attention and model parallelism. 3.2.1 Lightning Attention. We've designed a structure that allows us to calculate attention efficiently. This structure, known as linear attention, has a complexity of O(n)d squared, which means it scales with the size of the input and the square of the dimension. However, this method isn't efficient for causal prediction because it requires a cumulative sum computation, which slows down parallel training. So, during training, we stick to the traditional method of left multiplication. To speed up attention calculations, we've developed the lightning attention algorithm. This algorithm is designed to be friendly to input-output operations. It calculates an expression that involves the product of the query and key matrices, element-wise multiplied by an attention mask, and then multiplied by the value matrix. The attention mask allows for causal masking and positional encoding. In the lightning attention algorithm, we divide the input into blocks, move them from slower high bandwidth memory, HBM, to faster static random access memory, SRAM, and then calculate the attention output for these blocks. We then combine the results. This method speeds up computation by avoiding operations on slower HBM. We'll provide more details about the lightning attention algorithm in the future, including a faster method for calculating gradients. 3.2.2 Model Parallelism. To effectively train our large-scale TransNormerLLM model, we've optimized our system from various angles. When we say large-scale, we're referring to two things. The model has a lot of parameters, and the computational infrastructure has many GPU nodes. These factors present several challenges, such as GPU memory limitations, reduced computation efficiency, and slow communication speeds. Overcoming these challenges is crucial for successful large-scale training. We use the fully sharded data parallel (FSDP) approach to distribute all model parameters, gradients, and optimizer state tensors across the entire cluster. This strategy reduces memory usage on each GPU, optimizing memory utilization. To further improve efficiency, we use activation checkpointing, which reduces the number of activations stored in memory during the backward pass. Instead, these activations are removed and recalculated when computing the gradients. This method helps us compute more efficiently and conserve resources. We also use automatic mixed precision, AMP, to reduce GPU memory usage and speed up computation. Throughout our experiments, we use bfloat16 because it improves the training stability of large TransNormerLLM models. In addition to these efforts, we've optimized our system engineering by implementing model parallelism on linear transformers, inspired by NVIDIA's Megatron-LM model parallelism. Each transformer layer in the traditional transformer model consists of a self-attention block followed by a two-layer multi-layer perceptron, MLP, block. When using Megatron-LM model parallelism, it is applied separately to these two blocks. Similarly, in the TransNormerLLM structure, which also consists of two main blocks, SGLU and GLA, we apply model parallelism to each of them separately. We'll provide more details about our model parallelism strategies below. Section Summary. The lightning attention algorithm is introduced to accelerate attention calculations in linear transformers by splitting the inputs into blocks and loading them from slow HBM to fast SRAM, resulting in faster computation speed. Model parallelism is implemented using the fully sharded data parallel (FSDP) approach, activation checkpointing, and automatic mixed precision (AMP) to optimize memory utilization, improve computation efficiency, and reduce GPU memory consumption in large-scale pre-training of TransNormerLLM models. Section: Model Parallelism on SGLU. Let's discuss model parallelism on SGLU and GLA, and robust inference in the TransNormerLLM model. Firstly, let's recall the SGLU structure. It involves a mathematical operation where we multiply two matrices, X and WV, and then element-wise multiply the result with the product of X and W. The result is then multiplied by another matrix, W. In the model parallel version, we split the weight matrices WV and W column-wise and obtain an output matrix that is also split column-wise. This output is then multiplied by another matrix that is split row-wise. This process divides three matrix multiplications into SGLU blocks across multiple GPUs and only requires a single all-reduce operation in both the forward and backward passes. Next, let's look at model parallelism on GLA. Here, we have an operation where we normalize the product of three matrices Q, K, and V, and then element-wise multiply the result with another matrix, U. In this case, Q, K, V, and U are all derived from the input matrix X and different weight matrices. We use a combined QKVU projection to improve computation efficiency. The output matrix is then multiplied by a weight matrix that is split column-wise, similar to the SGLU structure. Now, let's discuss robust inference in TransNormerLLM. We have a formula that can be broken down into a form that allows TransNormerLLM to perform inference like a recurrent neural network, RNN. However, there's a potential issue with numerical precision due to a certain parameter being less than 1. To avoid this, we propose a robust inference algorithm. We simplify the formula by omitting a term and then use induction to prove a certain equality. We start with the base case where the equality holds. Assuming the equality holds for a certain value, we show that it also holds for the next value. Therefore, by induction, the equality holds for all values greater than or equal to 1. This means that both the original inference algorithm and the robust inference algorithm yield the same results. Section summary. The model parallelism on SGLU involves splitting weight matrices and output matrices along their columns, resulting in 3 GEMMs being split into SGLU blocks across multiple GPUs. This approach introduces a single all-reduce operation in both the forward and backward passes. On the other hand, the model parallelism on GLA splits the output matrix and multiplies it with a weight matrix split along its column axis. The combined QKVU projection is used to improve computation efficiency. Additionally, a robust inference algorithm is proposed to address numerical precision issues in TransNormerLLM, ensuring that both the origin inference algorithm and the robust inference algorithm yield the same results. Section 4 Corpus. We've compiled a vast collection of publicly available text from the internet, which amounts to over 700 terabytes. After processing this data using our specific method, as illustrated in the figure, we're left with a cleaned-up collection of about 6 terabytes, containing approximately 2 trillion tokens. We've organized our data sources into categories to make them more transparent and easier to understand. The details of these categories are provided in the table. In terms of data preprocessing, we follow a 3-step procedure: 1. Rule-based filtering, 2. Deduplication, and 3. A self-cleaning scheme. Before we include the cleaned-up data in our training corpus, it's evaluated by human reviewers. Let's talk about rule-based filtering. We use a set of rules to filter our collected data. Here's what we do. We start by removing HTML tags and web URLs from the text. We use regular expression techniques to find these patterns and get rid of them. This way, our language model can focus on the actual text content. Next, we get rid of any strings that don't add value, like strange strings or jumbled text. We have predefined rules that help us identify these types of strings and remove them. We also tackle the issue of repeated punctuation marks in the data. Having multiple punctuation marks in a row can mess up the natural flow and structure of sentences when we're training the model. So, we use a rule-based system to reduce these duplications to just 1 punctuation mark each. We handle special characters by identifying any unusual or special characters that aren't typically part of the language's text corpus. We either remove these characters or replace them with a standard representation. We standardize numbers. Since numerical figures can be presented in many different ways across various texts, we convert these numbers into a standard format to keep things consistent. We make exceptions for texts in Markdown and LaTeX formats when we're removing non-textual elements. These formats are structured and widely used in academia and documentation, so preserving them can help our model understand and generate text in these formats. Section summary. The authors gathered a large corpus of publicly accessible text from the internet, totaling over 700 terabytes, and processed it through a data preprocessing procedure to create a cleaned corpus of 6 terabytes with approximately 2 trillion tokens. They categorized their data sources for better transparency and outlined the specifics of these categories. The data preprocessing procedure involved rule-based filtering, deduplication, and a self-cleaning scheme, which included steps such as removing HTML tags and URLs, eliminating useless or abnormal strings, deduplicating punctuation marks, handling special characters, standardizing numbers, and preserving Markdown, LaTeX formats. Section: Deduplication. To ensure that our data is unique and to avoid the risk of overfitting, we use a highly effective strategy to remove duplicates. This strategy works at either the document or line level and uses 2 algorithms, min-hash and locality-sensitive hashing, LSH. The combination of these 2 algorithms allows us to balance the need for computational efficiency with the need for accuracy in the process of removing duplicates. This strategy also provides a strong method for removing text watermarks from our data. We also use a self-cleaning process to continuously improve the quality of our dataset. This process involves a cycle of 3 steps. One potential problem with using model-based data filters is that the filtered data may have a similar distribution to the evaluation model. This could significantly affect the diversity of the training data. However, if we assume that most of the pre-processed data is of high quality, we can train an evaluation model on all of the pre-processed data. This model will automatically smooth out the data distribution and remove low-quality data while keeping most of the diversity. Here's how our self-cleaning process works. 1. Evaluation model. We train a model with 385 million parameters on the pre-processed data. This model acts as a filter for data quality. 2. Model-based data filtering. We use the evaluation model to assess each piece of data based on its perplexity, which is a measure of how well the model predicts the data. Only data that scores above a certain threshold is kept for the next step. Any low-quality data is removed at this stage. 3. Human evaluation. We take a small sample of the filtered data and manually check its quality. We repeat these steps in cycles. Each cycle improves the overall quality of the data and ensures that the final model is trained on relevant, high-quality text. This self-cleaning process provides a strong method for maintaining the integrity of our data, which in turn improves the performance of the resulting language model. We also tokenize the data using the byte pair encoding (BPE) algorithm. To make sure our model works well with Chinese language content, we've added many common and uncommon Chinese characters to our vocabulary. If a word isn't in our dictionary, we break it down into its individual UTF-8 characters. This approach ensures that our model can handle a wide range of linguistic input during training. Section summary. The deduplication process in our study utilizes min-hash and locality-sensitive hashing algorithms to efficiently remove duplicate data and prevent overfitting. This combination ensures both accuracy and computational efficiency. Additionally, our self-cleaning scheme involves training an evaluation model on pre-processed data to filter out low-quality data, improving the overall quality of the dataset. We tokenize the data using the byte pair encoding algorithm, which includes a wide range of Chinese characters to enhance compatibility with Chinese language content. Section 5 Experiments. In our experiments, we used PyTorch and Trition to build our TransNormerLLM model within the Metaseq framework. We trained our model using the Atom optimizer and used FSDP to effectively scale our model to NVIDIA A180G clusters. We also made use of model parallelism where suitable to enhance performance. For our ablation studies, we trained all models on a subset of our corpus, which contained 300 billion tokens. To minimize the variability of losses and perplexities, PPLs, in the results, we calculated the average losses and PPLs of the final 1000 iterations as our final metrics. We conducted a thorough series of tests comparing our TransNormerLLM and the Transformer model across various sizes. The results, shown in a table, clearly indicate that our TransNormerLLM performs better than the Transformer. For instance, at a size of 385 million, TransNormerLLM outperformed the Transformer by a significant 5%. This performance gap widened to 9% in favor of TransNormerLLM when the size increased to 1 billion. We also compared the original TransNormer with our improved TransNormerLLM. The results showed that TransNormerLLM was not only 2% and 1% better respectively, but also significantly faster. In our positional encoding experiment, we compared LRPED, APE, absolute positional encoding, LRPE, and express decay, exponential decay. The results showed that our proposed enhancement already improved upon the original model. Furthermore, the final scheme showed a 2% improvement over the LRPE method. We also conducted ablations on the decay temperature, which is represented as 1L in the equation. Adding the decay temperature reduced the perplexity of the TransNormerLLM, as shown in the table. Section summary. In our experiments, we implemented TransNormerLLM using PyTorch and Triton in the Metaseq framework. We trained our model using the Atom optimizer and employed FSDP to efficiently scale it to NVIDIA A180G clusters. We also utilized model parallelism to optimize performance. Comparative tests between TransNormerLLM and Transformer showed that TransNormerLLM outperformed Transformer by 5% at a size of 385 M and 9% at a size of 1B. Additionally, in positional encoding experiments, our proposed enhancement showed a 2% improvement over the original model, and adding the decay temperature further reduced the perplexity of TransNormerLLM. Section: Gating mechanism. We carried out a series of tests to understand the impact of the gating mechanism in our model. Our findings, as shown in the table, indicate that the inclusion of the gate led to a decrease in the loss value from 2.263 to 2.247. We also experimented with the gated linear units (GLU) structure, specifically focusing on the activation function. The data from the table suggests that the choice of activation function doesn't significantly affect the final results. Therefore, we decided to use the 1 plus ELU function in our approach. We further tested the GLU structure by removing the activation function. The table shows that this change had a minimal effect on the final results. Consequently, we chose to use the simple gated linear units (SGLU) structure in our final model. We also explored different normalization methods, including SRMS norm, RMS norm, and layer norm, through a series of tests. The results show that these methods have similar effects when applied to TransNormerLLM. However, we made some improvements to the SRMS norm using Triton. As shown in the figure, our modified version significantly speeds up computations when dealing with larger dimensions, compared to the methods implemented in PyTorch. We compared the speed and memory usage of our lightning attention with the baseline, which is the PyTorch implementation of norm attention. The left figure shows the runtime in milliseconds of the forward and backward pass. Although runtime increases with sequence length, our lightning attention operates much faster, at least twice as fast as the PyTorch implementation. The right figure shows the memory usage of lightning attention compared to the baseline. The memory usage of lightning attention increases linearly with sequence length, but it's up to 4 times more memory efficient than the baseline when the sequence length is 8192. This shows that our lightning attention is highly efficient. Section summary. The inclusion of a gating mechanism in our model resulted in a reduction in loss value, indicating its effectiveness. The choice of activation function did not have a significant impact on the final results, leading us to select 1 plus ELU. Removing the activation function in the GLU structure had a negligible effect, prompting us to adopt the simple gated linear units, SGLU, structure. Various normalization methods showed similar performance, but our modified SRMS norm demonstrated improved computational speed. Our lightning attention outperformed the baseline PyTorch implementation in terms of runtime and memory efficiency, operating at least 2 times faster and up to 4 times more memory efficient. Section 5.2.1 Model Parallelism. We've conducted a series of tests using a 7 billion parameter TransNormerLLM model to examine how model parallelism affects the speed and memory usage of the TransNormerLLM. These experiments were performed on a single NVIDIA DGX node, which contains 8 A180G GPUs connected by NVLink. In these tests, we used FSDP and flash attention on the transformer. The results, as shown in the table, indicate that model parallelism significantly helps in saving memory. As we increase the number of partitions for the model, the memory usage per GPU decreases. However, due to NVLink limitations, we kept the model parallelism dimension to a maximum of 8 in all our tests. When we set the model parallel size to 8, the TransNormerLLM7B model only needs 24.1 GB of memory on a single GPU. This is a substantial memory reduction of 62.3% compared to when the model parallel size is 1. In contrast, the Transformer 7B model uses 28.7 GB of memory under the same settings. It's important to note that while model parallelism helps save memory, it only slightly reduces the training speed. The TransNormerLLM consistently performs much better than the Transformer. We also conducted stress tests on the model size and context length to evaluate the effectiveness of our system optimization strategy. We scaled the model up to 175 billion parameters, which is the largest version of the TransNormerLLM model released so far. However, training such a large model presents significant challenges. To effectively train this large model, we used a variety of distributed training techniques with the aim of reducing GPU memory usage and improving computational and communication efficiencies. To make training these massive TransNormerLLM models feasible, we used lightning attention, FSDP, model parallelism, AMP, and activation checkpointing. For the transformer models, we used flash attention in all experiments. Section summary. In the experiments conducted with a 7B TransNormerLLM model, it was found that model parallelism significantly reduces memory consumption per GPU while only marginally affecting training speed. The TransNormerLLM model outperforms the transformer model in terms of both memory conservation and training speed. Additionally, stress tests were performed on a scaled-up 175B TransNormerLLM model, using various distributed training techniques to reduce GPU memory consumption and improve computational and communication efficiencies. Section: Model Size. Model size and training experiments. Model size and training experiments. We conduct training experiments on different sizes of Transformer and TransNormerLLM models using a large-scale A180G GPU cluster, as detailed in the table. To maximize speed for different model sizes, we keep the context length steady at 2048 and increase the batch size until we hit the GPU memory limit. TransNormerLLMs consistently outdo their Transformer counterparts in terms of computation speed. This finding confirms the TransNormerLLM model's beneficial linear computational complexity, underlining its effectiveness. Context length and its utilization. Context length and its utilization. One of the key advantages of TransNormerLLM is its use of linear attention computation, which shows computational and storage complexities that are linearly related to the sequence length. To confirm this exceptional feature of TransNormerLLM, we carry out training experiments on Transformer and TransNormerLLM models of different parameter sizes. While keeping a batch size of 1, our goal is to maximize the context length. All experiments are conducted on a small cluster with 64A100 GPS. The results, as shown in the table, highlight the impressive long context length training capability of TransNormerLLM. Given similar computational resources, the TransNormerLLM model shows the capacity to train with longer context lengths compared to traditional transformer models, and it achieves higher computational speeds in doing so. Section Summary. In this section, the authors conducted training experiments on Transformer and TransNormerLLM models of different sizes to evaluate their computational speed. They found that TransNormerLLMs consistently outperform transformer models, demonstrating the advantage of TransNormerLLM's linear computational complexity. Additionally, the authors conducted experiments to validate the long context length training capability of TransNormerLLM and found that it can train with longer context lengths compared to conventional transformer models while achieving higher computational speeds.